a transverse wave is a wave that actually looks like a wave. It goes up and down like that. What are some ways you can calculate wavelength? Sean? Yeah, wavelength. I think that's what it says, right? Yeah, how can you measure the wavelength of a wave that's just standing there? It's just not moving for you. What would you measure? Yeah, the crests. So crest to crest would be one way. Trough to trough is another way, and there's one more that's not quite as easy to... Yep, for nodes. Every other node is going to be a full wavelength. So you've got crest to crest, trough to trough, and every other node. And I'll just show you an example of that quick, if I can get my wave machine to work here. There we go. What? That's working pretty good right now. So the first one that you guys mentioned was crest to crest, and that's true. So maybe you'd have a crest right here, and then the wave would go down. You'd have a trough down there, and it would come back up to another crest right there. So from here to here would be one wavelength. That would be crest to crest. The other one is trough to trough. If there's a crest right there, there'd be a trough down here. So you could go from trough to trough. So that would be another wavelength. So from there to there. And of course the other way is every other node. So from here to there, that would be one wavelength. Okay. Let's take a look at worksheet number 1. So there's a couple things that I want to talk about from this. Everything else I will leave up to you guys checking the answer key, which is on Schoology, because I want to make sure we have time to get through what we're supposed to do today. The first one is number 4. Let's take a look at problem number 4. It's on page 2. So basically what's happening here is the same thing that we did yesterday, or 2 days ago, with the slinky. I was on the floor, and Sean had it on the other end, and we were sending waves down towards each other. And in this particular example, it says the slinky is 5 meters in distance, 5 meters apart from each student. It takes 0.6 seconds for a transverse pulse to travel from the student generating the pulse to the lab partner on the opposite end of the slinky. So letter A, how long will it take for the reflected pulse to return to the student who originally sent it? What's that? 1.2? Not quite. This is just after it's going, this is like it went down one way. How long is it going to take to get back down? 0.6, yeah. Because remember, the speed of a wave doesn't change unless you change whatever that wave is moving through. And so if it takes 0.6 seconds to go down, it's going to take 0.6 seconds to go back. So letter A is 0.6 seconds. Letter D, or letter B, I should say. Now you're sending a second pulse down, and this one has twice the amplitude. Bless you. Bless you.
God bless you. God bless you.
Okay. Thought I was going to have to do a third one. You know, my wife sneezes like sometimes 14 times in a row.
Whoa.
It runs in her family. It's the craziest thing. My wife.
That's like scary.
It is a little scary. I think her record is 18 or so. Yeah. So it's the best when it happens like during a prayer or during a sermon at church.
Oh my God.
That's
I've done that a couple of times. I sneezed during a prayer and I just felt like the most unholy person. I was like, wow.
All right, so in terms of letter B, if you send a wave down that's twice as tall, it's got twice the amplitude, what's that going to do to the time? Is it going to make it longer, shorter, or the same amount of time? Don't think too hard. Remember, that's what I mentioned about this one.
Wait, if that has twice the amplitude.
Yep, twice the amplitude. Maybe longer. Did we change the medium the wave is traveling through? No. So that means the speed of the wave is going to stay the same. So this one is going to take the same amount of time. That's letter B. Then letter C. Now the students spread out, so they're further apart. So now the slinky that they're holding is more stretched out in the same way that it was more stretched out when Sean and I were using it in the back of the classroom. When we stretched that slinky out, did the speed get faster or slower? Got faster because we changed the medium that wave was moving through. And so because of that, we got a faster speed. And the same thing is true for letter C. The speed of the pulse will increase. Now letter D says, let's pretend we go back to the original orientation. Now you're 5 meters apart like you were at the beginning. And instead of sending down a transverse pulse, we send down a longitudinal wave, the one that's kind of like a compression that travels. So if that's what you're doing, how is that time going to change compared to the one that you sent down that was a transverse wave in the beginning? Is it going to stay the same? Is it going to change? Yes?
The same, because it's the same slinky, the same distance.
Exactly. So because we did not change the medium, the speed is not going to change, so it is the same. Very good. So that's number 4. Let's take a look at problem number 6. It's the other one I really want to focus on here. So this talks about Lake Winnebago, which is the lake I grew up next to.
Where's that at?
It's about 100 miles north of here in the Oshkosh-Neenah area. So you've got several docks. There's a crest at each dock, and it says that there are 3 crests between the 2 docks. So I got to draw 3 more of these little lumps here. 1, 2, 3. Not perfectly even throughout. If it was a really nice picture, all these waves would look the exact same. So you get the idea. From this problem, we know the distance between the docks is 40 meters. That's how spread out they are. And the first part of this problem asks us to figure out the wavelength using just this information. And that's something we can actually do. How many wavelengths are there from here to here? 4! 4 wavelengths, that's exactly right. So if our total distance is 40 meters, and there are 4 wavelengths over that distance, yeah, you just divide. So your wavelength is 10 meters. And that's letter A. Questions on that one?
Wait, can you explain it again?
Sorry, what was that?
Can you explain it again?
Sure. So we've got a total distance of 40 meters. And we want to figure out what the wavelength is from one wave crest to another. So in order to do that, we just have to ask ourselves how many wavelengths are there from beginning to end. And we can figure that out. Crest to crest, from here to here, that's 1. Here to here, that's 2, because that's another crest. Here to here, that's 3. Here to here, that's 4. So we've got 4 full wavelengths here. And if 4 wavelengths are spread out over 40 meters, you just divide those, and you get 10 meters as your total wavelength then. Letter B says if 10 waves pass one dock every 16 seconds, determine the period and the frequency. In your notes yesterday, when we were talking about period and frequency, I had you write down the units for each of those. Anybody remember what waves per second corresponds to? Does it correspond to period? Does it correspond to frequency? Or something else?
Period.
The V?
Period.
Maybe period,
What's the V?
maybe
Period.
frequency. V?
Period.
V is wave speed. So waves per second is telling you how many waves are passing by a certain point each second. In other words, how frequently those waves are passing by. So waves per second is a frequency thing. And that's something that you need to recognize in problems like this. Yes?
So then for the period, which isn't that like the time
Yeah.
that it tells? So what would that be?
That would sound like if it told you a certain number of seconds are passing by for each wave. Yep. So period would be the opposite. So this one is telling us there are 10 waves for every 16 seconds. So if that's true, and frequency is the number of waves per second, then we just divide the waves divided by the seconds. So again, frequency is the number of waves that pass by a certain spot every second. So if there are 10 waves for every 16 seconds, we divide those two numbers and out pops our frequency. Yeah, 0.625 is our answer. And the units on frequency are hertz. The follow-up question to this on the worksheet is, what's the period? Anybody tell me how we can figure out the period from this? Exactly. Yep. Yeah, so when we're calculating the period, if you know your frequency, you can automatically get the period. It's just 1 divided by it. So period T is equal to 1 divided by the frequency. That's in your notes. That's on your formula sheet. So if you've got your frequency, it's just going to be 1 divided by it.
Why is it 1 divided by 1 second or?
It's you're taking the inverse. So that's always going to be number 1 up in the numerator here. So if this was 14, your period would be 1 divided by 14. When you do that math, then it'll come out to be 6.25. No, never mind. 1.6, yeah.
Period.
That's right, that's your period. 1.6 seconds. Further questions on letter A or B? Okay, so now letter C says, what is the speed of the waves? And speed is something you can calculate because you've got the equation in your notes. You've got the equation in your formula sheet. On your notes from Monday, wave speed is V, and the equation looks like this. Wave speed V is equal to wavelength times frequency. On your formula sheet, it just looks like this. I don't know how you prefer to see these equations, but this is the same equation. 6.25 is the correct answer because we know our wavelength. Our wavelength is 10 meters. We know our frequency, that's 0.625. So we just multiply those together.
You could just move it in.
Yep. So yeah, you're just moving the decimal over to the right one spot. And that's number 6. So it sounded like some people were having issues with number 7. Let me just kind of give you a couple hints on that before I let you go with it and check the answer key on your own. So number 7, the first column on the left, you've got those two waves heading towards each other. So letter A, you're drawing them right before they collide, so those two bumps will just be a lot closer. And then letter B, it says what happens during the collision. Well, remember, when two waves collide, the result is just a combination of those two shapes. So if you've got one wave that's 3 meters high and one wave that's 3 meters underneath, when they're right on top of each other, those are going to even each other out and cancel out. So the letter B for that would just be a straight line. Letter C then, because they pass through each other, the wave on the top would be a little bit to the right after the collision, and the wave on the bottom would be a little to the left after the collision. So that's what you would get for the left side column for number 7. The right side column is the same thing, but now because the waves are on the same side, they're both on top, when they collide, they'll make a wave that's bigger. That's the only difference. Yes?
Okay, so if they're coming at each other, they go through,
Mhm.
right? And then if it's one on top, one on bottom, and going opposite, it's just a straight line.
Yeah, they still go through each other, but because one wave might be a certain height up here, if the one going the opposite way is the same height underneath, it's like when they're in that same location, for that brief moment, they're going to cancel each other out.
Right.
Yeah.
And then if they're going the same way, it's just one big wave.
Yes.
Okay.
Yep. Okay, I'm going to come around and grab this from you, and then we'll do some old things and put a new spin on them. Thank you. Thank you very much.
It's like it's popular.
Thank you. Yes. Thank you. Yep. Thank you. Yes.
That's not so complicated. Like in front of
Well, because we're exploring the possibilities of physics and waves. Thank you. The deeper you go in anything, the more complicated it's going to be. Thank you. Thank you. All right, we are going to take some notes today. So loosen up your hands and title your notes. Reflection and refraction revisited.
Reflection and refrain.
What's that? Reflection and refraction revisited. Alrighty. So here we go. Hopefully part of this looks a little familiar to you. Let's say we've got two different mediums here. And maybe there's a ray coming in like that. And it makes a 55-degree angle with respect to the vertical there. We'll say that the top medium is air and the bottom medium here is water. So the top is the fast medium, the bottom is the slow one. What direction would this ray go as it goes from one to the other?
Down.
It's going to go down, exactly. So it's like you have your light ray coming in, it's in the fast medium right now, and then it gets to the slow one. So this front right tire is slower, the front left tire is faster, and that's going to cause it to turn downwards. Maybe something like this. And if we wanted to, we could use Snell's law to figure out what that angle is going to be. The angle it makes in the water. You can copy this down if you like, but you don't have to work through it on your calculator. Snell's law was mostly last chapter, but I just want to briefly touch on it here. So again, this was last chapter. This is not something you'll be tested on in this chapter, but I just kind of wanted to have it out there so we know that we've seen this before. We know that if we go through the calculation, we'll find that this angle is actually less than this top angle up here. But here's the new part. Instead of thinking of this as a beam of light, we can also think of this as a wave. And the way that you draw waves on this kind of a picture is you have to have each wave be perpendicular to the ray. So start by just adding some waves to your ray. And again, all you got to do is make sure that they are perpendicular to the ray that's going down like that. In this kind of an example, the ray just shows the direction the waves are moving. It makes it very easy for us to see what direction they're heading. That's why this ray is there. If you just had these, it would be kind of hard to tell exactly where they're going. Now you can also draw waves down here. And here's the main thing you have to remember about all this. As long as you know that the waves are perpendicular to the ray, you're halfway done with drawing these correctly. The final step is remembering and knowing that when you're in a slow medium, the wavelengths are more scrunched together. Your wavelengths are smaller in a slower medium. So down here I would draw my waves. Bless you. Bless you.
No more.
I would draw the waves closer together, and that's the idea. If I wanted to, I could also draw reflection. It's up to you if you want to put this in your notes or not. It's pretty straightforward. I could draw a reflection of this and say that these waves are also reflecting. If you ever have to deal with reflection, as you would probably guess, this is all the same medium. It is all the same wave speed. So all the wavelengths should be the same distance. It's only when you change your medium that your wavelengths are going to change along with the wave speed. Questions on this so far? So number 1, draw your waves perpendicular to the rays. Number 2, if it's a slow medium, like water, wavelengths are close together. If it's a fast medium like air, they are more spread out. We'll go through 2 examples. Yeah, that's about it. And these next 2 examples aren't even going to have numbers. How do you like that?
Yes.
Now let's draw the difference in mediums vertically, because they're not always going to be horizontal. That would just be too easy. Yeah, it's going from a slow medium to a fast one. When you draw these rays, you're going to want to use a straight edge on the homework. So now the question is, what direction is this ray going to go? Now again, in this example, we're talking about waves here. This is not a beam of light now. We're talking about light and how it behaves like a wave. So these are waves that we're dealing with. So as they're heading in this direction, what direction will they turn? Will they turn down or will they turn across? Down, exactly. Because it's like the car moving in the slow medium. Now it moves into the fast one. So this tire, the front left, is moving quickly, causing the car to turn down. The ray and the waves will follow suit. So now this is a fast medium. Am I going to draw the waves so that they're more spread out or close together?
Spread out.
Very good. That's exactly it. That's all there is to this.
All there is to this but to do it.
What was the last thing you said?
I said the only thing to it is to do it.
That's right. And I got one more example to show you then, once you're done with that. Let's say we've got a fast medium on the bottom, slow medium on the top. That means the wavelengths and the fast medium are going to be more spread out. And on your homework, when you get it, one set of wavelengths will already be drawn in. So it's just a matter of making sure that when you draw the next round, they're either bigger or smaller than what you start with. You don't have to draw both sets. I'll start with that. So we've got waves that are decently spread out, moving in the fast medium. And maybe in this particular example, we're supposed to show 2 things. Maybe we got to show reflection and refraction. If we would have to do that, I would start by just drawing another ray that actually reflects. And you would want that ray to have roughly the same angle here as it had going in right there. You would want those angles to be about the same. The other thing you'd want to be about the same is the wavelength, because this medium is all the same medium. So your wavelength should be the same in both. Now there's something else interesting that kind of happens with this. If we're going from fast to slow and we want to show refraction, is this going to bend up or is it going to bend across? It's going to bend up. Very good. For the exact same reason as before. The car comes in and it's going to turn upwards. It's just how it works. So I would draw the other ray going up.
It's kind of like a lightsaber.
Yeah, a little bit. So here's the fun part. You see how these waves are along this interface here, the difference between the mediums? If you start your waves right here and you draw them so that they're perpendicular to this ray, they're just automatically going to turn out to be nice and close together, which is exactly what we would expect in a slow medium. All you're doing is starting from these spots and you'd want to draw them perpendicular to this line. So if I do that the best I can, they all just kind of come out that way. It's not perfect. If I used a straight edge, it would look a lot nicer and cleaner. But you get the idea. The point is that if you do this correctly, you should be able to check your work with this and see if these waves are actually, coming out to be closer together or further apart. But again, the main thing I'm looking at for this is that your waves in a fast medium are spread out. Your waves in a slow medium are closer together. Okay. I'm going to pass out the homework. On Schoology, it says it's due tomorrow. That's because it sort of is. We're going to be going through it at the end of the hour, but you're going to have the hour to work on it. So you don't have to have this done when you get here tomorrow, but it would be nice if you kind of got started on it. I won't be checking to see if it's done at the beginning of class. You'll want to have a good enough start on this though so that you can finish it by the end of the hour. So make sure that you do a couple at least. You're welcome. The final thing that I'm going to show you here So again, if you go on Schoology, there's all sorts of nice resources for you there. If you want to check out the rest of the answer key for the worksheet that you turned in, it's just in this folder. Light and sound is where we are right now. So if I open that up, I'm going to find the chapter we're in now. That's Light as a Wave. And remember that these little yellow boxes are walkthroughs. So if you want a quick walkthrough at your own pace of what we just did in class today, you can go ahead and do that. So we've got these waves here, and again in our examples that we do, The rays are just there to show us the direction that the waves are heading. So I can use this to show a little bit of reflection if I want. You'll notice these wavelengths are the same distance as these wavelengths. That's what you're looking for if you're in the same medium. If you're going to a slow medium, it says slow if I move this thing. If I go to the slow medium then, we would of course expect those wavelengths to be closer together. And whenever I do that, you can see they just naturally end up being much closer together when they're aligned in that spot right there. And then I just do it where you can actually just show one wave at a time going through as a little animation. So again, that's everything we did in class. You know everything you're supposed to know. Draw them perpendicular. Fast, medium, they should be spread out. Slow, medium, close together. The end.